welcome to Aerohive's end-to-end QoS, or no QoS at all, presentation. QoS is an acronym for Quality of Service, which you likely already know or you wouldn't be watching this highly technical video. My name is Devin Aiken, though my friends call me Devinator, and I wanted to spend a little time talking about implementation of QoS in a Wi-Fi infrastructure. Let's take a look at a few other QoS-related topics involved in the controller-based scenario. As you may have heard, many vendors have implemented what is generically referred to as airtime fairness. This is a process by which data frames destined to clients are given appropriate airtime based on the link speed of the client, rather than sending one frame to each client in a manner consistent with the 802.11 standard. The 802.11 standard implements an arbitration mechanism that is often referred to as packet fair, but this mechanism causes all clients communicating with an AP to get the same throughput as the slowest client, regardless of each client's link speed. Instead of a scenario of one packet for you, one packet for you, one packet for you, some vendors have implemented a system whereby each client gets the same amount of airtime or appropriately unfair amount of airtime, and so more data can be transmitted to faster clients during the same amount of time. Airtime fairness is recognized by all vendors as the most advantageous way to handle multiple client environments. Each vendor has their own brand name for airtime fairness, and Aerohive's name is Dynamic Airtime Scheduling. It was named due to the granular mechanism that we've implemented in each access point. That brings me to an important point, and that is, who does the microsecond by microsecond downlink scheduling of airtime for each of the clients associated to the AP? In Aerohive's solution, there is no controller, and so all functions are handled by the Hive APs. It's important that scheduling of the airtime happen quickly with the ability to make instantaneous changes because the RF environment is dynamic. RF obstacles move, clients move, interference sources come and go, client density changes rapidly at times, there may be SLAs in place for clients and groups of clients, and there's of course much more. With all these changes and requirements, the only way to appropriately dole out airtime is at the access point itself. Controllers are milliseconds away and simply cannot react fast enough to these dynamic RF environmental changes to be effective and to optimize throughput for each client. With 802.11ag, the controller wasn't typically a bottleneck because 802.11ag APs were just not capable of producing that much throughput and were generally not that busy anyway because of the state of applications at that time running over the Wi-Fi network. 802.11n, however, changed the game forever. High-quality 802.11n access point radios can produce nearly 200 megabits of throughput each, and with the upcoming 3 spatial stream radios, that number will jump to nearly 300 megabits of throughput per radio. With an average of 2 radios per AP, that's 400 and soon to be 600 megabits of actual throughput headed toward a controller for every access point. In large enterprise installations with hundreds and often thousands of access points, even several racks of large controllers could not keep up with that kind of throughput demand. The controller model simply breaks, and all the QoS in the world can't keep the applications happy. An additional QoS issue is that WMM is very coarse. We will address that in a later slide, but it's worth mentioning now because there was room for that bullet point on this slide. You have to get your punches in wherever you can, right? Okay, so this is what I've been building up to. It's the original model of 802.11 QoS, meaning QoS at the edge. Remember FAT APs, aka autonomous APs? Well, there were lots of good things about autonomous APs, despite what controller vendors will tell you. Certainly, they had issues with fast secure roaming and radio resource management, but when it comes to handling QoS, they were quite good if the features were implemented properly in each access point. Aerohive's APs, called Hive APs, implement control plane functions such as fast secure roaming and radio resource management in software rather than in hardware because protocols scale better and are more resilient than controller hardware. That allows our architecture to benefit from the QoS, security, and RF controls that need to happen at the network edge, rather than trying to pseudo-handle them at the network core. While Hive APs can be connected to the Ethernet network via trunk or access connection, it's highly recommended by experienced network designers to use trunk connections. This allows for distributed forwarding, unlimited scalability, low latency, and end-to-end QoS. Implementing controllers as an opaque network overlay has, as you've seen, many drawbacks. This is the reason that many of the controller vendors are now moving to a fully distributed model where controllers will be in the mix only for the purpose of being an application layer gateway. Eventually, controllers will go away altogether because they are simply unnecessary. Yes, you can quote me on that. If you can do something in software, it simply adds too much cost, complexity, and failure points to implement it in hardware instead. There are a few Layer 3 aware Layer 2 switches in the market that can read DSCP tags and use them to mark the uplink 802.1p fields in the Ethernet header, but they are rare and typically very expensive. As you can see from the drawing, in Aerohive's model, all network segments have both Layer 2 and Layer 3 QoS markings. There's an old saying about network QoS, it's either end-to-end or not at all. This applies to Wi-Fi QoS as well. When moving from a fast switched network like Gigabit Ethernet to a much slower shared medium like 802.11, good QoS is not just a nice-to-have feature, it's absolutely essential. Think of it like moving from a 4-lane highway to a 2-lane highway. When it's not busy, it's not a big deal. But when it's crowded and a voice frame ambulance needs to get through, it's life or death for your applications. Prioritizing downlink traffic at the controller rather than at the AP is like trying to prioritize cars, trucks, and ambulances miles ahead of where they will have to be put into the proper order on the highway. Looking at the graphic, would you prioritize traffic at the red X or at the green checkbox? I think that's called a rhetorical question. Let's move along. Remember me mentioning that WMM isn't enough? Well, it isn't. It's a decent mechanism, but it's far too coarse to be highly effective in densely populated, highly loaded, and greatly varied RF environments. One significant problem is that of dropped 802.11 frames. When congestion happens, frames get dropped. When frames get dropped, it almost always causes upper layer retransmission. In the case of TCP, that means that TCP window sizes are cut in half or worse, which literally destroys network throughput. For this reason, Aerohive has implemented a traffic classifier, policer, marker, and scheduler in each Hive AP. Ingress traffic is assigned to a user profile, classified into 8 queues per user, rate limited per user profile, per user and or per user queue, and then queued into those 8 queues per user. The scheduler optimally determines when each frame should be put into the WMM queues so that no frames get dropped. An additional advantage to this QoS scheme is that user profiles and queues can be weighted for preference and implemented with either strict queuing or weighted round robin queuing for additional granular prioritization. This allows APs to maintain SLAs for each user on the network. Thanks for attending Aerohive's QoS presentation. We hope this has been helpful. Please visit aerohive.com/register to check out our free Wi-Fi network planning tool and Hive Manager online, and have a great day.